All right, thank you, Jim. Good afternoon. It's great to be here. Thanks for having me out, Jim. I tell people this is my favorite week of the year, even better than Christmas. That's how much I geek out on this stuff. So I'm happy to be here, be a part of this, and get a chance to see friends and colleagues and talk with students and people trying to learn these methods that I find fascinating. So I'm going to talk about stochastic actor-oriented models. Just a brief overview here, I think. Okay. Huh. We're not progressing here. All right, there we go. All right, so yeah, I want to talk a little bit about what is a stochastic actor-oriented model. And the key thing here is this actor orientation, is if you can understand that it's an actor-oriented or kind of an agent-based model at its heart, then it makes the model very, very easy to understand as well as all its extensions. And then I'm going to spend some time talking about how Siena models capture network influence, talk a little bit about some kind of review of basic network influence ideas, and then extending that to some new ways of modeling network influence that these models have allowed in recent years. And then some trade-offs between some different ways of operationalizing and measuring influence. Okay, so let me start just by thinking about the idea of what a Siena model is trying to do. Okay, so let's say we've got a network observed at one point in time, right? And then we've got observed at a second point in time, and maybe there's future additional waves of data. What we're really trying to do is understand how do we go from this network to networks that look like this one and later waves. And the Siena model asks the question really is what selection mechanisms lead to networks like we observe across time. Okay. And so Jim talked a little bit about ergms earlier today, and the Siena model is in many ways the same thing. We take a basic set of effects and say, what if actors use these kinds of effects to make changes to their ties, make changes to their network, and then we simulate that across time and look to see, do we get a network like what we observe at later waves? So what we're really trying to do is again, fit a model to networks observed at later time points, starting at the first network we observed. So we might have a model like Scott was showing, where we've got homophily in there, and reciprocity, and transitivity, right? These other kinds of, within the Siena framework, these are all rules that actors use. Okay, so actors are given a chance to change their network, and they use these different rules to decide which tie they're going to change, if they're going to add a tie, if they're going to drop a tie. Okay, and so we're kind of modeling this process across a number of waves. Okay, so a Siena model, I'm going to call it a Siena model. They've had multiple kind of personalities over the years, right? At one point they were a stochastic actor-based model. Now the terminology is a stochastic actor-oriented model. They're all the same model. The Siena model is really the software that's used to estimate the model, so it's not really a description of the model itself. Now a Siena model is an R Siena model because it's in R. Okay? But what it really is it's a model. We're modeling panel data across time. Okay? So we've got these observed kind of sociocentric networks. Okay? We've got them observed at least 2 points in time, but we could have additional waves as well. And what the Siena model is going to do is assume that between these observed waves, we have a large number of microsteps. And it's across those microsteps that the network is actually changing. So the network is changing from time 1 to time 2, one step at a time, one tie at a time. And so we might have 100 or 1,000 microsteps between any two observations. And within any of those microsteps, the model is giving a randomly selected actor a chance to change one of their ties. Okay, so we've got a network of 100 actors, right? Any given microstep, one of those actors is randomly chosen, and that actor looks across all possible ties. Some ties are present, most dyads are empty in the networks we study, and makes the change that's going to kind of produce some kind of positive utility, right? Maybe add a reciprocated tie or a homophilous tie or transitive tie, do something. And then another actor gets a chance to change their ties. Okay, so what this looks like, let's see if I can pop this up here, is if we've got our network at time 1 that we're conditioning upon. Oh, you can't see that, can you? Let me jump out of here. Okay. All right, if we've got our network at time 1, oh, come on now. Okay. What we're doing is randomly choosing an actor. Okay, and let's say, right, this one in red is the one chosen. That actor looks across all potential ties, and what does it do? It adds a tie. Okay, and then we go on to another actor, right? Randomly choose another actor. Here it's this one in red. That one looks across the network. What does it do? It does nothing, right? It's happy with its state, kind of the state of its network world. Okay, then we've got a actor up here. Give them the chance. They've dissolved the tie. Okay, and so this goes on and on and on. Again, thousands and thousands of times. And what we're trying to do, again, is these actors are using these rules to try to decide which ties to add and drop. And we're coming up with parameter estimates associated with those rules. So how important is reciprocity or homophily in the decisions that actors are making? Okay? And which of these are, when we obtain a fitted model, what we're really saying is that we have a set of parameter estimates that when actors follow these rules, when transitivity is weighted a certain amount, homophily is weighted a certain amount, when actors follow these rules and we simulate a network, we get a network at time 2 that looks a lot like the network we actually observed at time 2. Okay, it's got the same properties as that network. Okay. Now, this actor orientation really helps the Siena model to be very flexible, okay? Because instead of just looking at one network and how ties are changing across time, we can bring in a number of other outcomes. Okay? So we could bring in a second network. Okay? So for instance, we could bring in a network of status relations and look at how friendships evolve, how status relations evolve, and then look at how those two influence one another. Okay? We could bring in an outcome that's a behavior, something like smoking, or any other kind of attitude, or something we want to predict change in, and we could bring in a third behavior, a second or a third behavior. Okay? We can even bring in a two-mode network, such as individuals joining organizations, and model how those ties change across time. Okay? We could bring in each of these as its own outcome, and within the model itself, again, what we're saying is an individual actor is given a chance to make a change, and they choose among these different outcomes what to change. They might change a friendship tie, they might change their smoking behavior. If we've got organizations that they belong to, memberships in the model, they might change a membership. And the model allows us to have endogenous effects between these, right? So friendships can change based upon kind of the behaviors my friends are exhibiting. Okay, so if my friend starts smoking and I'm not a smoker, I don't care for that, I might dissolve that friendship. Okay, if I start smoking, I might add smokers as friends. Okay, so my smoking status can change my friendships. My friendships can also change my smoking status through network influence. Okay, so all of these things kind of change endogenously, which is really the advantage of the Siena model over a lot of other models that might have exogenous changes between these things, but not model them in conjunction like that. So here's a kind of a typical Siena analysis. This one has two outcomes. It's got BMI as an outcome, and then a friendship network as an outcome. And we have a number of effects. Here's the friendship function over here. We're predicting friendship. Again, things like transitivity and reciprocity, being in the same grade, co-participating in sports, other activities together. All those things predict friendship. Okay. This paper itself was interested in BMI and the effects of friends on BMI and vice versa. So over here we have how BMI affects friendship, and we see that, what do we see? Ego effects for BMI, so students with a higher BMI sent more ties, but also BMI similarity. Okay, so students who were more similar on BMI tended to be friends across time. Okay, so we're predicting the effect of BMI on friendship over here. Simultaneously, we're predicting BMI. Okay, and we've got a number of kind of traditional controls in the model, none of which really seemed to matter. The main thing that mattered was friend influence. Okay, and we see a positive effect of friend influence, meaning that students tended to adopt the level of BMI that the friends, the people they nominated as their friends, had. Okay, so here we see evidence of both kind of the peer influence on BMI, the friend selection on BMI, and had MEMS been around, how long ago was this? 12 years. We could have done a MEMS to really partition out how much each is responsible for similarity on BMI, but we did not do that. Okay, so that's kind of what a typical Siena model looks like. Okay. Now I want to talk a little bit more about behavior change and network influence. Okay, and so with the conventional Siena model, we take whatever behavior we're interested in and we turn it into an ordinal variable. Okay, something with somewhere in the range of 2 to 10 levels. Okay, and the idea here is that actors are changing their level of a behavior. They're really taking steps. They might go up a step to one higher level of the behavior. They might go down a step. They might stay the same. But on any given kind of micro step in the model, they're only moving their behavior at most one level up or down. Okay, they can make bigger changes across time, but that requires more micro steps. Okay, so effects in our model represent, do actors tend towards higher levels of a behavior? Do they tend towards lower levels? Do they tend towards somewhere that's where their friends are? Okay, these effects don't necessarily represent increases or decreases across time, which is I think a little bit different if you're coming from more linear modeling, where you see, for instance, this effect here, right? It's a positive effect. This doesn't necessarily mean that people increase their BMI across time. Right? This positive coefficient means that actors are more likely to change their behavior such that it brings them closer to their friends. Okay? That might be an increase, that might be a decrease, but they're moving to be closer to their friends. Okay, so all right, and I've got an illustration of that in just a second. What I want to, why I bring this up is that I think it's important to kind of step back and think about, when we're talking about network influence, what is it we actually think is happening? How do we think this network influence is occurring? We've got all kinds of different processes that we talk about, right? We've got modeling and reinforcement, status seeking, like all kinds of different ways that people might change their behavior, in response or because of other people. We rarely measure these processes, at least in the network world, right? We don't measure them. We measure kind of what they look like in the network, kind of their structural imprint in the sense of how a network and behavior changes from one point in time to another point in time, and what kind of network configurations lead to certain kind of changes in a behavior. Okay, we can think about these structural imprints along 3 dimensions. Okay, one is someone might change their behavior based upon the behavior of others in their network. Okay, so I change my eating behavior based on what my friends are eating. Okay, it could be the network structure. Something about the network structure is changing why someone changes their behavior. I might start eating a lot because I don't have friends, and I'm depressed about that, right? So it's not anything about what my friends are doing, right? It's that my network position is one of being an isolate. Okay? So we can think about a lot of different network configurations that might change, lead to changes in behavior, and then we can interact these two with one another. Okay, and so I'm going to talk about a few of these just to get us thinking about the different ways influence can occur. Okay, so this is an example of, in Siena, what's called a similarity effect. And what we have here is an example of, we've got two people, okay, and their level of smoking, one person's up pretty high, one person's down pretty low. So the mean of the population, let's say, is right here. The friend's mean is right here. With this kind of a similarity effect, when it's present, what actors are doing is they're changing their behavior to be closer to their friends, right? And so some people, that's moving down, right? If they're already at a high level and their friends are lower. For other people, that's increasing, right? So in this case, friends' behavior is kind of an attractor point, and that differs across every individual, right? Because people have different sets of friends. Some may be going, smoking a lot because their friends do. Others may be dropping down. That's all represented in this one, what's called a total similarity effect. Okay, and notice this is irrelevant of the population mean. Okay, so it's all the local context that's driving changes in behavior. Okay. Another kind of, so this, I should mention, this is probably the most commonly used influence effect within a Siena model. Okay, is a version of similarity, one that this one doesn't weight by number of, this one weights by number of friends. You could also look at one that's not weighted by number of friends. So by contrast, we have what are called alter effects. And these are effects that look at, again, take the same individuals, and here the comparison is between where are my friends relative to the mean. Okay? And if my friends are at a higher level, if my friends are smoking more than the average level of smoking in the network, then kind of among my friends, smoking is more normative, right? And that we think that kind of behavior is being reinforced. In that case, individuals, this effect captures individuals increasing their behavior. Okay, so person B is increasing, which brings them up to their friend's mean, but person A is increasing, which is taking them away from where their friends are. Right? So it's a very different kind of influence. Okay? It works different across actors. This first kind of influence can create this simulation where if you imagine a connected network, eventually everybody converges on the same level across a long period of time. This one can lead to polarization, right? Because people whose friends are above the mean are pushed up. People who have friends whose smoking is below the mean, those people are pushed down. And so you get very divergent kinds of or a bimodal distribution of the behavior in the network. You can. That's the pressure. Okay. All right, some other kinds of content forms of influence. So I should mention, if you estimate Siena models, you start working with these things called short names, which is kind of how the effects are referred to when you identify them in the R software. And so this min x alt captures the idea that people try to keep up with their friend that has the lowest level of behavior. They don't want to be an outlier and have the lowest level, right? So they're at least going to have in the case of smoking, for instance, they're going to smoke as much as the lowest smoking person in their network. Okay, we could have a max version of this that means people respond to the behavior of their highest smoking alter. Okay, that those are the most influential. We can also look at things like this total alter distance 2 is looking at what friends of friends are doing. Okay, and this could be if I want to impress one of my friends, I might look to see what their other friends are doing. Right? These are the people that they're friends with. They respect their behavior. I might adopt the behavior of my friend's friends as a way to kind of impress or maintain the friendship that I have. Okay. We also have effects that look across different kinds of attributes. Okay, so this av x alt effect says, does a tie to a person or alters with certain attributes lead to changes in a different attribute on my part? So, for instance, does contact with another ethno-racial group other than my own change my attitudes towards intergroup contact? Okay, so these are all looking at content in different ways, scattered kind of across a local network. Some structural sources of influence, right? So we've got, if being an isolate affects one's behavior, how many friends one has, right? How many people are naming one as a friend, how many people one names as a friend, that kind of sociality might affect certain kinds of behavior. We can also get kind of group structure, local group structure. We're having friends who are friends with one another. That closure, that triadic closure, that might have effects on things like feelings of cohesion and solidarity and belongingness. It might also be kind of a moderator of peer influence. For instance, having those tight-knit networks might really enforce norms. Whatever the group norm is gets reinforced there. Okay. So those are all kind of main effects of network content, network structure. I want to mention moderation as well, just because it's possible, but with the caveat that it's Santa models are notoriously low-powered for measuring change in behavior. Okay, so that's measuring change in behavior. Even with main effects, they tend to be low-powered. Okay, if you want to bring in interactions to test some kind of moderation, they're even more low-powered. So it's really hard to test these kinds of things, but with a large enough network or a strong enough effect, you can get these. And so these are just some examples of some of the kinds of interactions of, we might want to get. I mentioned stronger peer influence in triads. We could also think about, are some people more susceptible to peer influence? Are certain kinds of people with perhaps low self-esteem, or other people who are younger, in a network with older people, are they more susceptible to peer influence? Are some kinds of people more influential? Or questions about kind of the peer influence within kind of in-group dyads versus cross-group dyads. Right? We could imagine that those differ. Okay, so these are all kind of this is just a handful of the different kinds of ways we can measure network influence. So how do we choose what to do? Well, theory. Right? We start with theory. What do we think? Again, how do we think network influence is operating? Who are the alters that we think are influential? And what are the network structures that contribute to that? And then we sift through all the possibilities within our Siena to try to find the best way to represent those. Okay. All right. That was a very cursory overview of Siena. So I'm saying if anybody has questions, I'm happy to answer them along the way. Or I will keep going and shift gears a little bit now. Yeah. Yeah, I mean, I think there is certainly other streams of work that look at kind of peer influence, either in natural settings, more qualitative observational studies, or laboratory studies looking at specific kind of mechanisms. And we're just kind of building on. We know these kinds of things happen, and if they happen, this is what they would look like in network data. But I think it's a big ask to do all of that in one study. I mean, it would be a big study, but you could imagine, for instance, if you have a field site, you're talking to people, and you're really trying to understand local customs norms and how status systems, and you might gather some network data to kind of operationalize some of that as well. Yeah.
There are a whole series of field experiments for folks who are doing this kind of thing, as well as the lab experiments. So there are a lot of these things that the key with them is that because they're so narrowly focused on key mechanisms as experiments, they tend to be ungeneralizable. So it's pretty awesome.
Similarly, there are a lot of animal behavior studies that don't have the same language, but are absolutely the same. That's a definition of novel dominant hierarchy. Qualitative research is
All right. Other questions? I'm gonna totally switch gears. All right. Okay. So what I want to talk about is categorical outcomes, which is something that Siena models they don't categorical variables don't really align with the conventional way that Siena models a behavior, unless it happens to be a dummy variable. But otherwise, the kind of classical categorical model, you've got 3 or 4 or 5 or so categories. It just doesn't work when you've got this level of the behavior that you're trying to model. And so the solution for that is what, I don't know if you covered two-mode networks the other day, but it's a two-mode network where we've got actors as rows, and we've got outcomes, possible outcomes as columns. I'm going to talk about 2 ways that we can think about bringing in a two-mode network. One is with kind of the classic categorical variable where there's mutually exclusive outcomes, and every case, every individual falls into just one of these categories. And then cases where we've got non-mutually exclusive outcomes, and some interesting things that we can do there. Okay, so here's a paper actually we wrote a couple years ago, looking at health lifestyles as an outcome and trying to understand selection and influence on health lifestyles. And the first thing we did here is we assigned this is AdHealth data, so these are students. Assigned them to one of to different health lifestyles. We did a latent class analysis and found three lifestyles: healthy, unhealthy, and then this discordant that was a mix of healthy and unhealthy. And then at 2 points in time, we assign each student to one of these lifestyles. Okay, so in the data, it kind of looks like this. We've got students at time 1. Student 1 is in this discordant lifestyle, and time 2, they are unhealthy. Student 2, they're unhealthy at time 1, unhealthy at time 2. Right, and so we represent kind of change over time through these two-mode networks. Okay, and then our question, really, the question we had was about peer influence. And so within a two-mode network, the way we get at peer influence is, so what we're looking at here is do friends, so friendships are represented by an arrow between. The circles here represent students, okay, and the triangles here are a lifestyle. And so when peer influence occurs, what we expect is that students who are friends, when one student selects a lifestyle, the friend will select that same lifestyle. And so we see that pattern across time. Okay, so what we're looking at really, right, is this is the outcome, the pattern that we're interested in, and does this kind of increase the probability of this tie in the two-mode network being either being formed or persisting across time. Okay, now we have to control for selection, right, because networks can change, lifestyles can change, and so here in this case, the selection argument is that having the same lifestyle prompts friendship, right? People who are smoking and doing other risky behaviors are more likely to encounter one another and develop a friendship, whereas people who are avoiding that might also be encountering one another and developing a friendship. So here we have 2 students selecting the same lifestyle at time 1, and then we've got the friendship between them developing at time 2. Okay, and so in our model, we would have an effect for the former effect for peer influence, predicting what lifestyle people adopt in the two-mode network. We'd have this effect in the model for friendship, predicting how friendships develop. And we're estimating those jointly. Okay, so all right, so that's kind of the basic idea of peer influence within a two-mode network. Now, sometimes we have data that's not a traditional categorical variable, but we have multiple indicators of some outcome of interest. Okay, so oftentimes, I don't know if we have any psychologists here, we have a scale or an index where we have a number of items, right? And when we do something to turn all those items into a single composite that we then use to measure the outcome of interest. Okay. Now that kind of data could be treated in different ways by a Siena model. Okay? The conventional approach is to kind of do what we do normally, is we create that composite measure. Within Siena, we have to turn that into an ordinal variable. Right? So if it's this nice numeric number, we create some kind of ways of turning it into a few ordered categories and then apply our model. There is a Siena model that will model behavior as a continuous outcome. That's still new. There's not a lot of work yet that uses it. It's not quite as well developed in terms of what you can do, but it's out there. Okay. Another approach that I'm going to talk about is using a two-mode approach that takes those separate indicators and models them separately. Okay. So what we're doing here is something like this. We've got individuals here, right? Our actors are individuals, and they can kind of be attached to multiple items or multiple entities from this scale. Okay, so this is what our how our two-mode network looks like. So we have individuals connected to entities. They might be connected to one, more than one, to none, meaning they, if this is, well, I'll give you an example in a second. But our goal here, right, is to model over time how do these ties between actors and the entities that they're connected to, how do those change? Okay, so some examples of this kind of data. Many of us in this room have looked at students and extracurricular activities, right? Where we have students and the kinds of activities that they might belong to. Again, they might belong to multiple activities. They might belong to none. We could also look at, there's an interesting paper recently that asked students open-ended questions about what are you interested in? Just tell me what you're interested in. And then went in and did some qualitative coding to put these into a number of categories and then kind of modeled that change across time. A health example would be this recent paper on malaria prevention behaviors, right? And this is a paper that looked at, I forget what country this was in, but they talked to villagers, all villages within members of a village, and asked what malaria prevention behaviors they used, right? Do you use these nets with insecticide? Do you wear covering clothing? Do you wear boots? Do you wear gloves? And someone could do all of these, right? Or none of them, or some of them. Okay, and again, the conventional approach, right, might be to count these up. How many do people do? But what we're saying is we can look at these separately. And so let me show you how this differs from the categorical variable example. Here's an example of a categorical variable, right, where everybody is connected to one outcome. Okay, if we've got 3 outcomes, right, healthy, unhealthy, discordant, every student's connected to one of those, and that's it. So there's not a whole lot interesting structurally here, right? The kinds of effects that we're interested in are like ego by alter attributes. Are there certain kinds of individuals that are drawn towards certain kinds of outcomes? Not a lot interesting structurally, but we can model this within Siena. Okay. Here's the case when we have individuals connected to multiple kinds of entities, right? We've got some that are connected to 2 or 3 different entities. Some of these are connected to just one, some are connected to none. But we get some complex kind of interdependencies between actors and those entities that we can model. Okay, so one example here would be we can look at influence through co-affiliation with the same entity. Okay, so for instance, members of one extracurricular activity might influence, co-members might join other activities together. All right, so here we've got 2 actors, part of the same activity. This one's a member of a second activity, so this one joins that across time. Okay, that would be an example of kind of this, again, having one behavior in common or one outcome in common leads to having others in common. This is one way to kind of get at the bundling of behaviors, like with the health lifestyles, or if we think of other kinds of kind of contexts where different sets of behaviors go together. This helps to represent that kind of process. Another kind of influence could be if actors are selecting entities that other people like them selected. Okay, so in a paper we looked at on extracurricular activities, we see that people who are, in this case, the nodes, they're both shaded, meaning they share some attribute. Okay, so if one joins this activity, the second one joins it across time. So you can think of this as kind of looking around and someone asking themselves, what do people like me doing? Like what activities or behaviors is someone like me doing? And then adopting those same behaviors as others. So again, a kind of a modeling kind of process at work there. Okay. Now, so when we've got multiple indicators, we could model them in different ways, right? Again, we could take the conventional approach where we create a scale, right? If this is malaria behaviors, we create a scale and or prevention behaviors, I guess, and then we model does someone increase or decrease their behaviors across time. Or with a two-mode approach, we look at which specific behaviors does somebody enact, and how does that change across time. Okay. Now we can do answer some of the same questions with these approaches, but we could also do some very different kinds of things. So here is the example with the malaria prevention behavior, right? A traditional approach might be to just sum up, right? For every person, how many of these behaviors do they enact? And then we model this as an outcome. Okay? The two-mode approach takes all of this, right? All this two-mode data, and looks at which specific behaviors are individuals enacting, and how does that relate to their network. Okay? So some things we can get at with both approaches. So the conventional approach, if this is what we're seeing, right? A and B both engage in 3 behaviors. With the conventional approach, this scenario looks the same as this scenario, right? A and B are both engaged in 3 behaviors. So in the conventional approach, those 2 scenarios look the exact same. Okay? If we use a two-mode approach and model this as a two-mode network, but we're looking at, we can look at the out degree in the two-mode network. We see that both A and B have out degree of 3. Both A and B have out degree of 3. These 2 scenarios look the same if we wanted to model kind of the extensity or sociality in that two-mode network. Okay? Alternatively, we could look at which specific items these actors are selecting. Okay? And here we see that again, A and B are each selecting 3, but they're the same 3. Right? They've got complete overlap in what they've selected. So in this scenario, this two-mode specification captures that overlap of 3. In this scenario, it captures that overlap being just 1. Okay, so we're capturing something different there. And what looks like, again, with these 2 specifications, this looks like a case of homophily because they have the same level. When we look at the actual behaviors, yeah, they're both engaging in the same extent of malaria prevention behaviors, but they're doing very different things. Okay, and so that we're able to capture that kind of insight. Okay. Okay. So, and kind of thinking about the differences between these 2 approaches, kind of creating a composite measure versus those separate items. Measuring peer influence on the level of a behavior, how many. We can do that in both. You know, here it's what level is someone at. Here it's out degree in a two-mode network, but we can get that. If we wanted to measure, do people move to the same level as what their friends are doing or the people they're connected to, we get that with the similarity effect in the conventional approach. That's currently not something that's possible in our Siena. It's I don't know why. It's conceivable. We could think of an effect that could do that. It's just nobody's bothered to program that as best as I could tell. Okay. Now when we move on to peer influence on specific items, we can't do that with a conventional measure. Right? If you've got a composite of how many behaviors someone is engaged in, you can't just take that number and know what items lead into that number. So we can't get that, but we can get that with the two-mode network. All right. And again, I want to mention these do kind of tap into a little bit different kind of processes. Right? We can imagine on specific items that this could be, we could imagine that happening through modeling, kind of seeing the behaviors. It could be information diffusion about specific behaviors, where to get certain resources. I can't see that far back. What is that? That is 0? Okay, all right. This can be. Yeah, no. This will be one more slide to go. All right. This kind of, when we're looking at levels, that maybe gets some other kinds of ideas of influence, more about maybe norms. There's still, it's still fuzzy. You can't say this effect gets at this kind of theory, but there is a closer alignment between some theories and some measures of influence. Okay. Now there are some things that, other kinds of effects though, that really differ in what we can do with a conventional versus a one-mode approach, or two-mode approach. We can ask with both approaches, do certain kinds of actors engage more in this activity? Right? This kind of sociality effect in the two-mode network, or in the conventional network, just are some kinds of people at higher or lower levels. We could also, with the two-mode network, look at heterogeneity in these items. So are there certain kinds of items that make them more common or less common? So in case of malaria prevention, some of those might be really expensive, right? Some might be really cheap, right? And so you would expect those that are really cheap to have a lot more in degree, kind of all else being equal. And so you can model that heterogeneity in specific items that makes them more or less attractive. We can also, with the two-mode approach, get at complementarities. So are certain kinds of people more likely to adopt certain kinds of practices, for instance? So you could imagine, maybe there are religious differences in the kinds of practices that one engages in. So for instance, contraception or something, where you've got individuals of different religious groups, right, modeled as an ego attribute, and then different practices modeled as an alter attribute, and you can look at that interaction. And then you can also look at constraints on the data. So there are all kinds of cases where certain kinds of people aren't allowed to have some kind of outcome. Okay, so in some research that I've done, other research I've done looking at multiracial youth, thinking about race in the US, people without, well, let me just say, you can only choose a race in the US if your ancestors somewhere belong to that race. You can't just pick any racial category. So if you want to model what racial outcome youth choose, how they choose to self-identify, they have to choose from their family ancestry. And so you need some constraints on the data because people can't choose something outside their ancestry. And that's something that's really easy to do within a two-mode network. And I'm out of time, but you can peek ahead to a couple slides to see how to do that. So. All right, thank you.